So today I wanted to discuss this theorem. A group of order 9 is abelian. There are some advanced tools that we can use that will make this problem very easy. But today I wanted to discuss this only with some less advanced tools. So first, the order is 9. And using Lagrange's theorem, we know that every non-identity element has order 3 or 9 because I'll write it down, Lagrange's theorem. So for all x in G, order of x will divide the order of G. And then since the order of the group is 9, that will imply that order of x has to be 1 or 3 or 9 for all x in G. And then this first case is only possible if and only if x is the identity element. And then we're not really sure what happens in the other two cases, so we will break them down to two cases. The first case is there exists an element in G such that the order of x is 9. And as you can see, this case is pretty simple because the order of x is 9. This implies that the order of the cyclic group generated by x is also 9, and that means G is just a cyclic group. And then we know that a cyclic group is always abelian, so we're done here. So what about the other case? So the other case, if there is no element in G that has order 9, that means every non-identity element has to have order 3. So this case is all non-identity elements have order 3. Yep. All the non-identity elements have order 3. And then the goal of this theorem was to show, we wanted to show that G is abelian. So what we want to show is for AB equals BA. But so let A in G be given. Then the goal here is to prove that for all B in G, AB equals BA. Then since A was given here, that would imply that for every AB in G, AB equals BA. So there are a few cases. The first case being if A equals the identity element. This case, I think it's pretty clear that AB is going to be just B, and this is BA. And the second case is, oops, I forgot to do one more step. Going back a little bit. So the goal was to show that for all B in G, AB equals BA. So to do that, let's pick some B in G. So A and B are given, and then if we can prove that AB equals BA, that means for any pair AB, we get AB equals BA. So now we break this down into a few cases. A is the identity. Then it is pretty clear that AB equals BA. The second case is B is in the cyclic group generated by A. That means B equals AI for some I in Z. Then AB equals AAI, AI plus 1, then AIA, BA. Therefore, we get AB equals BA. So these two cases are pretty simple. The third case is actually a lot more complicated, unfortunately. So if B is not in the cyclic group generated by A, and then A is not E either. So if we can show this, if we can show that AB equals BA, we're good. So this is the last case, and then we just want to show that, I'll just write it down here, show that AB equals BA. This is our goal. And then since this is the last step, if we can show it here, that means AB equals BA in general. In this case, when all the non-identity elements have order 3, so that means that this is the last case. Then if we can prove this, we'll be good. So first I'll give you guys the outline of how we're gonna tackle this part. First, we're gonna show that using these two elements, A and B, we will show everything in G. So the first step, outline, show that AI, any element can be expressed as AIBJ for some I and J. So this is the key, AI B to the J. So as long as we're gonna first show that any element in G can be expressed as product, and then we will argue that this implies BA equals AIJ for some IJ. And then we will show that I and J both have to be 1. Then this clearly implies that BA equals AB. So this is like kind of the outline of what we're gonna do. So how we are gonna proceed here is, so we're gonna use the fact that each non-identity element has order 3. And then from the way we chose A and B, it is pretty clear that A and B are both non-identity. That means the order of A and then the order of B, they're both 3. So if we're gonna do this A to the I, B to the J thing, then that means I and J have to be, they just have to be between 0 and 2. So 0, 1, 2. So let's see. So we have these elements. So if I goes from 0 to 2 and J goes from 0 to 2, then we will have 9 elements, right? So 3 by 3 equals 9. The problem is, so if there are 9 elements, then we are expressing everything in G. But the problem is is there any duplicates? So if a to the I, b to the j, there are some pairs of I and j such that a to the I, b to the j become the same thing, then that's not good. If that was the case, we wouldn't have 9. But I just realized that it's 9. Some people might think it's a factorial, so I'm just not going to do that. So suppose AI1 bj1 equals AI2 bj2 for some I1 j1 I2 j2 for z3. Then this would imply that AI and from the way we have found A and B, or from the conditions that we know about A and B, it is clear that this implies I1 equals I2, and then J1 equals J2. So for that, we're using the fact that first, B is not in the cyclic group generated by A. And then also the fact that A is not the identity and then B is not the identity. So this argument implies that there are no duplicates. So this argument achieves the first goal, that is, we can express everything in G as A to the I and B to the J. So that means B to the A is clearly A to the I for some A to the I and B to the J for some I and J. And then to show that I and J have to be both 1, we kind of have to go case by case. But if you think about it, so there are 9 possible cases, but we actually don't really have to do all of them, because if you think about it, BA cannot possibly be E from the way we chose B and A. This is clearly not A or B either, because otherwise one of A or B would be the identity element. So the questions are A squared B, AB squared, and A squared B squared. These are the 3 elements that could possibly be equal to BA. So for each of them, we kind of have to tackle each of them separately, but A squared B, if this is the case, then this would imply that BA A squared B, BA equals BA to the third. So basically I'm just multiplying BA from each side. And if you look at it, this A cube will turn into E. And now we have 1, 2, 3 B's. So this whole thing will turn into E. So the left side, will turn into A. And then this one is clearly E, because every element has order 3. I mean, every non-identity element has order 3. And then A and E cannot be equal, so it's a contradiction. And then now, what's AB squared? I'm gonna move this guy a little bit here. So for AB squared, we can take a very similar approach. AB squared, BA, this would imply that BA, AB squared BA equals BA cubed. And if you look at it, BA squared, B cubed, A, this disappears, then this disappears. So this part is gone. So, and then the right hand side will be just E. So this would imply that B equals E, and then this is a contradiction. The last one, A squared, B squared equals BA. This would imply that A squared, B squared, B equals A, B, A, B. And then now we have A cubed, B cubed equals AB squared. And this means E equals AB squared. By Lagrange's theorem, the order of AB has to divide 9. That means order of AB is not 2. That means that would imply that AB is the identity, which is also a contradiction. So the only possible element is just A to the I, B to the J, or should I say A to the 1, B to the 1. So just AB. So in each case, we proved that G becomes abelian. So as long as if you have a group and if you know that the order is 9, then we know that that group has to be abelian.